We'd like to look at subroutines. Subroutine is a program fragment that performs some useful function. Subroutines help organize a program. Subroutines should have strong cohesion. That means they perform only one specific task. Subroutines should be loosely coupled. That means it's interfaced to the calling program through parameters where possible. Not affected by changes to other subroutines. Subroutines keep the program smaller. Subroutines are much easier to maintain. Instead of fixing 6 places in your program where you do the same thing, you only have to fix one. It reduces development costs while increasing reliability. There's fewer bugs. Copying code repeats bugs. If you miss one place where you copied code, you're in trouble. Subroutines are often collected into libraries of subroutines. So let's look at how the call mechanism and return mechanism works. So without subroutines, you have this program over here. First you do task X, then task A, then task Y, then task A, then task Z, then task A, then task W. Notice that task A got called 3 separate times, or got done 3 separate times. You could replace task A in line like that with a subroutine. And it would kind of work like this. So you make a subroutine, you do task X, then you call task A, then you do task Y, then you call task A, and you do task Z, then you call task A, then you do task W. And you only have one piece of code now to maintain and to write that gets called multiple times. So you can see it uses less program memory. So the advantages: smaller programs, easier to maintain, reduces development costs, increases reliability, which means there are fewer bugs due to copying code, and it's more library friendly. The advantages, on the other hand, without subroutines, is it's faster and less overhead. So how does the subroutine linkage work? A subroutine is called in assembly using the MSP430 call instruction. The address of the next instruction after the subroutine is saved by the processor on the stack. Parameters are passed to the subroutine, usually in registers or on the stack. Local variables are created on the stack at the beginning of the subroutine and popped from the stack just before returning from the subroutine. At the end of a subroutine, an RET instruction, which is a pseudo instruction actually, pops the top value from the stack into the program counter. So let's look at some stack operations. So you can do push B or W source, which basically puts a byte or a word on the stack. The stack pointer is advanced 2, and the new stack pointer, the source is put in the stack pointer, wherever the stack pointer is pointing on the stack. So basically that pushes a byte or word on the stack. Call, that's a subroutine call to a destination, and you can see there what happens on the stack. If you look at that closely, the program counter ends up being stored on the stack. A return from interrupt, RETI, actually returns from an interrupt. An interrupt is a non-synchronous subroutine. In other words, it could happen anytime. A return instruction is an emulated instruction, and that's what you use to return from a subroutine, and basically it pops the instruction address from the stack pointer into the PC and increments the stack pointer so that you go to the address after the call that caused you to go to this subroutine. And a pops a byte or a word from the stack. So when you push something, you need to pop it. You need to, if you push it at the top of the subroutine, you need to pop it before you return, otherwise you'll go to the wrong destination. So here's a quiz for you. What is the value of the stack pointer after the second call to delay, and is there a problem with this program?